Okay, welcome to Lab 4, the Aldol Condensation, the last virtual lab of Chemistry 222. We chose this lab as a virtual lab as there's not a lot of new experimental techniques learned. There is a recrystallization that is done, and we do use a centrifuge to isolate some extremely fine particulate matter. However, this experiment is more important because of the mechanism and the underlying theory that controls this experiment. Now, the aldol condensation has not been covered yet in lecture. However, if you review the mechanism on page 14 of the lab manual and understand that the enolate is acting as a nucleophile and the ketone or the carbonyl is acting as electrophile, you understand the essence of an aldol condensation.
The general mechanism for an aldol condensation is given on the top of page 14. The specific mechanism for this reaction is given just below. Follow the arrows, and again, you'll understand how the nucleophile attacks the electrophile, followed by a dehydration, leading us to the final enone.
The novelty of this experiment perhaps lies in the fact that it is solventless. As explained in the lab manual, both of the starting materials have very low melting points, and as a result, they act as co-impurities, and upon mixing, without any solvent, they liquefy. The addition of a catalytic amount of sodium hydroxide causes the nucleophile to become charged, reacting with the electrophile, producing a large molecule that has a high melting point. Once this forms, we get solidification, and then we isolate through use it as a centrifuge and then recrystallization. At this point, we'll move over to me carrying out the experimental procedures. You'll watch this synchronously with your entire class, and at the end of the video, you'll reconvene with your laboratory instructor to discuss any issues you may have with the experiment, any questions you may have, and clarify the requirements for the laboratory write-up.
Okay, so here we're going to start the solventless aldol. It's a bit of an odd reaction simply because we don't use a solvent and we take advantages of the melting points of the two starting materials being relatively low, and then when we mix them, we end up with a material that's actually a liquid, a homogeneous mixture. So the first reagent we're going to use is 0.25 grams of the dimethoxybenzaldehyde. Need about 0.25 grams. You can see, though it's a solid at room temperature, the melting point I think is in the low 40s, high 30s degrees Celsius. We are going to try to do a yield calculation in this lab, but you'll see a little later that the transferring of this material is sometimes a little difficult. Also, we're going to do a recrystallization. Oh, there we go. So we're going to record that as 0.25 grams of the benzaldehyde. All right, so I'm going to transfer that into our reaction vessel, which is a good old-fashioned garden variety test tube. All right. All right. The indinone, again, very low melting point material. We need 0.2 grams of that. And again, you can see that it's a light brown color, probably suggesting a small amount of impurity. So both the starting materials are likely impure. The Merck index describes both of these compounds as a clear, clean, or a white crystalline material. This is not quite white. I don't know if the camera's picking that up. Beige is probably a better descriptor. And again, we'll have to do a yield calculation, a limiting reagent calculation to determine the yield of this material. Okay, we're trying to get fairly close to these amounts because it's almost a stoichiometric amount of material. All right, so we're going to transfer that into our test tube. All right. All right, two solids. All right, more or less similar in nature. And then what I'm going to use is just a good old-fashioned glass stir rod, and I'm going to muddle this together, okay? And what you'll see shortly is that this material starts to merge together, okay? Process takes a little bit. I don't know if you can see it's starting to change color a little bit, and these materials are actually starting to melt to one another. Effectively, what's happening is we have one of the reagents acting as an impurity for the other reagent. So if you've got a melting point of, say, I don't know, 38 degrees Celsius, and you add a lot of impurity to it, of course the melting point lowers and broadens, and so it becomes a melting point below room temperature. So we've been at it for about 10 minutes now. Hopefully the camera's picking it up. We've got a clear brown oil with a small amount of solid material in the bottom of the test tube. It's important that everything be fully dissolved before we add the catalytic sodium hydroxide. It gives everything a chance to react. So we'll fast forward through some of this. It's a little tedious, but we do want to make sure that everything's fully dissolved in one another. Again, each compound acts as a co-impurity, or they're acting as co-impurities. We're almost there. Okay, so that's probably the better part of 10-15 minutes, and we do have everything nicely dissolved. Okay, so now what we're going to do is we're going to weigh out some sodium hydroxide. That's the catalytic amount. Introduce it to get the reaction going. The sodium hydroxide will cause a deprotonation of the indinone, and then the indinone acts as a nucleophile to react with the benzaldehyde. Again, it's a catalytic amount of sodium hydroxide, so as best we can, I'm going to try to put in 0.05 grams of sodium hydroxide. We have a titch more, 0.06, but again, it's intended as a catalytic amount. Take a look at the mechanism and you'll understand why it is a catalytic amount. Right? Okay, so we're going to be transferring the sodium hydroxide to the test tube. Because of static electricity and the fact that sodium hydroxide is hygroscopic, meaning it picks up moisture, sometimes that transference is a little difficult. So I'm going to aid that with a little bit of help with a spatula and transfer the material that way. Okay, there we go. So I've added the sodium hydroxide and off we go. Okay, now the key to this part of the experiment is we keep this thing moving. As the reaction occurs, we're going to start to get solidification, all right, and then it has a hard time dealing with fusing itself to the bottom of the test tube. As this reaction proceeds, we go from a liquid to a solid, effectively freezing of the material, right? We get a reaction forming, so two molecules become one molecule. That's going to be an exothermic process, where the dissolving was an endothermic process. We expect this to get hot. Now, it's not going to be massively hot. We don't have a lot of ingredients here, but that's a good indication of when the reaction starts to kick or starts to go forward. All right, that'll also coincide with the solidification of the material. Okay, so we've been mixing for about 3 or 4 minutes. You can see that the solution is starting to become murky. It is starting to warm to the touch, so the reaction has started to go. And again, okay, the murkiness is really starting to develop now. And that is the production of the large molecule, the large final product. I am going to try to keep this moving as best I can, because if I don't, what happens is you get a very solid plug of material and it's very difficult to work with. I'm going to keep moving it so it's easy to transfer out. Okay, bit of time travel. We're another 2 or 3 minutes down the reaction time. We're getting close to the end of the reaction. You can see that this material has now turned into a really thick paste. Okay, another 2 minutes in, and we have got a nice thick paste of material. All right, it's very gummy in consistency. Okay, give it another minute or so, and then we're going to add some sodium some HCl to finish the dehydration and end up with our final product. So I'm going to transfer this material in here. Okay, so the best we can do, all right, you can see we have a solid plug of material here. We do have some glass shards there. That's going to be fine. I'm going to transfer that in a few moments to a secondary container, but clearly this test tube is past its best before date, and I am going to now transfer the last little bit of some material. But you can, maybe the audio is picking it up. That stuff is really pretty solid at this point. But again, you can hear that that stuff is really almost welded itself onto the side of the test tube. Okay, and that's certainly what led to the incident with the broken test tube. Okay. So we've done a reasonable job of transferring the material to a beaker. Again, quite solid. Going to be careful here. I'm going to add 2 mils of HCl, and that's going to do the last little bit of reaction. All right. This is not a graduated pipette, but again, we just need enough material to neutralize the sodium hydroxide. And I'm going to, just as a rule of thumb, a full pipette is worth 2 mils. I'm going to actually add approximately 3 mils. Okay. And very gently over the next few minutes, I'm just going to break this material down, giving this reaction a chance to complete. Okay, so after a little bit of frustration and some novel approaches of using a stir rod as a pistol, we've been able to pulverize this material quite convincingly, producing a large surface area and allowing the acid to interact with the insoluble final product. This is the final dehydration reaction forming an enone of the final product. We're going to test the pH to make sure it's acidic, and then once that is, we're going to try to separate that material using a centrifuge. And we have a pink or red litmus paper. This solution is nicely acidic. So I am sure that under the mixing and the stirring and the crushing of the solid that we've been able to complete the final dehydration reaction. All right, so this material is going to be transferred into a centrifuge tube, and the fine solid is going to be separated out. Okay, so I've assembled one of our centrifuges, and the reason we're using a centrifuge, it may not be perfectly obvious, but in years gone by, in the analysis of this material, it's extremely fine, and it does tend to clog up filter paper. It's not an unreasonable suggestion that we would separate the liquid from the solid using vacuum filtration. It's just in previous experiences we found that this doesn't work very well. The filter paper clogs, and it's really an exercise in frustration. This seems to work quite well. So I'm going to be transferring this material as best I can into a test tube. And using very small amounts of water to help with that transference. And again, loss of material through transfers is probably a legitimate observation here. So for the most part, things are fairly well established. You know what, I'm going to use a second test tube to get that last little bit. All right, so give myself a little extra room. Oh, the added benefit here is I'll be able to use both test tubes. One is the as a counterbalance to our centrifuge. All right. We're missing one of the rubber feet, apparently. They don't get used that often. We used to use them quite a bit in first year. All right, letting it spin down slowly. And we can see that the material is nicely settled to the bottom. All right, that's the first test tube, second test tube, and we're good. Now what I'm going to be doing is removing the liquid, transferring the solid to a small Erlenmeyer flask, and we're going to be doing a recrystallization. Okay, so I've assembled some material. I've made up approximately 50 mils of solution of ethanol water mixture. That's going to be my recrystallization solvent. I have my 2 centrifuge tubes. and I'm going to be transferring the solid into a recrystallization flask, Erlenmeyer flask. Careful eyes might see that I think we have a small amount of glass left over here from a small accident. We can deal with that a little bit later once we've done the recrystallization and filtered out our material. Okay, so to start with, I'm just going to discard the water into a waste beaker. All right, so now I've got our two solids of our product. I'm going to transfer that into a 50 ml Erlenmeyer flask. What I'm going to do now is, just because I'm not going to be able to remove all the material with that spatula, I'm going to use a small amount of the recrystallization solvent and just rinse the test tube out. Okay, and this I think will work fairly well to get rid of, or to transfer of that smudgy material. All right? And then this I'm going to pour out. Now, the manual suggests that we use no more than 20 mils of solvent to recrystallize, so I can actually use a fair amount of the recrystallization solvent to transfer over the material. Now, what I'm choosing to do is I'm going to leave a small amount of this material behind purposefully, because I'd like to take a crude melting point of this material. It's always a good idea when doing a recrystallization to take a melting point of your crude material and then your pure material. And then, if the numbers are comparable, i.e. the crude material isn't that crude, you know in future steps that the recrystallization isn't going to be required. So what we're planning to do is here purposely take we're going to dry this and take a melting point of this later, crude, and then we're going to compare that to our purified recrystallized material that we'll have in a few minutes. Okay, so hot plate, couple boiling chips, and we'll do our recrystallization from here. Okay, so I've got the stuff transferred onto the hot plate. It's warming. It'll take several minutes. And again, a reminder, we always use an Erlenmeyer flask for recrystallizations because of its conical nature. The vapors are hard. We don't lose nearly as much through evaporation because the conical shape of the flask helps condense the vapor and reintroduce it back into the solution. All right, so with the boiling chips, we'll give this a few more minutes and see what happens. Okay, so we've been heating for a couple minutes now. You can see a lot of the material is starting to dissolve. We've got a bright yellow liquid or supernatant over top of the crystallized material. What you can do here carefully, if you just rotate the flask at a bit of an angle, you can help rinse down some of the material that was stuck on the neck of the flask. Now, that's not ideal, it's not perfect, and what we'll find is when we get a little closer to boiling, the vapor is going to evaporate, or vapor is evaporated. It will condense on the flask and actually rinse down some of this material into the container. All right, so we will get a chance to dissolve all of that material. Okay, we're in about another minute or two, and you can, if you look closely, you should be able to see the flakes starting to dance. That's an indication that the solvent is just about boiling. It's just boiling now, almost a simmer. At this point, we have to be kind of careful. If the evaporation occurs too quickly, we could end up frothing this material out of the flask, and that's no good because we'll lose a lot of our material. Also, at some point, the conical flask won't be able to condense all of the vapor, and we're just going to lose it. So we're trying to dissolve all of our material at this point, with the understanding that perhaps we haven't added enough solvent. If we continue to boil it, temperature's not going to get any hotter. If the solids, when it's boiling vigorously, we won't dissolve more material through more heating. In fact, what we're going to be doing is chasing our tail, because we'll just be losing more and more of the solvent, making it more concentrated and harder for it to dissolve the final little bit. All right, so it looks like we have reasonably good boiling here. And at this point, it still looks like there is a modest amount of material undissolved. So I am going to go ahead and add a couple more pipettes of solvent. That ensures that the solvent that we're losing through evaporation is replaced, but it also adds a little extra solvent so that we can ensure that we dissolve all our material. So that's 2, 4. I'm going to add another 6 mils of solution. Okay. So at this point, I believe I'm upwards of around 20 mils of solvent. Okay. Now this is just an approximation, right? I'm using the marks on the Erlenmeyer flask, which are notoriously inaccurate, but it is, again, it's going to be ballparkish. So in my notebook, I'll write down approximately 15 mils initially, followed by an additional 6 mils to in the dissolution of the material. Now, we can't be too specific with this because, again, we are losing material through evaporation, and recrystallization is always done sort of as a needed amount, right? You watch the process. If you have to add a little bit more, you add a little bit less. An exact volume measurement isn't actually that useful. It's just kind of doing it by eye. All right. All right. Now, it looks like we still have a few boiling chips in there. Those will not dissolve. Those are the big chunks in there. And for the most part, I'm just going to add 2 more pipettes worth. And what doesn't dissolve in that 2 mils, those extra 4 mils, I'm just going to leave. But you can see here, a couple large boiling chips. Hopefully that's picking up, and just the smallest number of flakes of undissolved material. Okay, so I'm going to bring that up to a boil, stop it, cool it, ice it, filter it, and we'll be done. Taking the flask off the hot water, or sorry, off the hot plate rather, and letting it cool for probably a good 5 minutes before I ice the solution. Okay. Okay, so things have settled for probably 10-15 minutes in an ice bath, maybe a little longer than we needed to. On close examination of the solid, it is extremely fine. All right. From experience, if we try to filter this, it'll probably be met with frustration. It will just clog the filter and we'll be stuck watching it. So choosing to be proactive here, we're going to transfer this into test tubes, and we're going to centrifuge it down and use the trick that we used in the initial step to try to isolate our material. Okay, so we ran it down for a few seconds and you can see things settle out quite nicely. We've got our solid material here, and I'm just going to use that clear liquid above it to help transfer that last little bit of solid into other test tubes. Right. If I were just to use more and more solvent, what you would do is eventually dissolve more of your material. So you're actually chasing your tail again because you're doing extra work to transfer material over, but in fact only making things worse because you are dissolving more material than you're actually transferring over. So I'm going to do this a few more times to hopefully transfer over the last bit of material. I'm going to be balancing out the test tubes a little bit so there's approximate volumes are the same before I do the last centrifuge. Okay. There we have it, our isolated material. So all that remains to be done now is to remove the liquid above, isolate the solid, let it dry to take a mass and melting point for yield calculations. So at this point, I'm just going to be pouring out the liquid from the centrifuge. You can see that the liquid is actually yellow in color, so we do know we're losing some material because of solubility. Some material has simply just dissolved and isn't coming out of solution. So that points to the fact that you always do lose material with recrystallization. But by comparing our crude material versus our purified material, we'll see if the effort was worthwhile. If we get a pure product, great. We expect a small loss of material. However, if the purity of the crude material is similar to the recrystallized material, we are really just doing extra work for no added benefit. All right? And that's the reason why we take the crude melting point and then a purified melting point. So in future, we know if our efforts were required or done in vain. All right? With the aid of a little bit of solvent, I've been able to transfer the material into a beaker, at which point I'm just going to let it evaporate over the week, isolate the material, take a mass, and then melting point.
After allowing the material to dry for several days, the material was reweighed and melting points were taken of both the crude material that was not recrystallized and the purified crystallized material. The mass of the final isolated purified material was 0.41 grams. The melting point of the crude material that was not recrystallized was 165 degrees to 172 degrees. The final product that was purified had a melting point of 177 to 180 degrees Celsius. Please include these values in your lab report and make the appropriate conclusions. The spectroscopy associated with the starting materials and the products can be found on your Moodle page.
All the things that I did. You need to understand.
I have to hear one more time that you did this for the family.
I did it for me. I liked it. I was good at it.